Hey, hello everyone. Okay, this video going to introduce also the statically indeterminate but in torsional load member. Okay, it's very similar to axial loaded member. We also have the statically indeterminate torsional torque load member. Okay, actually, it's very similar to what we did in axial loading. Okay, so it's the same, almost the same example. So assume we have a cylinder bar and confined in the two walls, A, B, and the terminal point is called A and B. And then we apply a torque. We apply a torque. Okay, the amount of torque, the amount of torque is 500 Newton times meter. Apply the torque here, and we want you to we want to ask you to calculate the torque at A and B. Okay, so TA and TB. So yeah, okay. I just say it's TA and TB. Sorry. Okay, sorry. Okay, so this is also very typically statically indeterminate problem, but in torsional load member. But the concept is the same. Okay, so in such problem, after you use the you need to find another equation to solve the problem, and so it's so-called compatibility equation, or mathematically speaking is find another constraint for this problem. Okay, so let's start to draw a free body diagram of this problem. So he say we show you this is rod AB here. AB, here's rod AB. Okay, and here's A, here's B, and you want to calculate the torque at the terminal points, torque A and torque B. So actually it's the same as we did the axial loading problem. Okay, I don't know the direction of the torque, if I don't know the direction of the torque, I just assume every torque is counterclockwise. Okay, remember that. Okay, if you don't know the direction of the torque, just assume every torque is counterclockwise. Okay, so I just assume the torque here is counterclockwise, the torque here also counterclockwise. Okay, so I can call this TA and I call this TB. Okay, yeah, I have a different assumption from the textbook, but trust me, you will have the same answer finally. Okay, and there is external loading here, external torque here, and it's counterclockwise. Okay, counterclockwise. Okay, 500 Newton times meter, and the distance here is 3, and distance here is 2. Okay, so, okay, first of all, we use the rigid body equilibrium, and in this problem, we only have the torque applied on this system, so we only need to we need to only consider the total moment balance. We don't have to consider force balance because force is zero equal to zero, so that's useless. So the total moment of the system is equal to zero. Okay, so the torque here, so I assume everything is positive, right? So every torque is counterclockwise. So we'll have TA, and the torque here is 500, is counterclockwise. So we have 2 plus 2, 500, and plus TB and is equal to 0. And we'll have the equation like TA plus TB equal to minus 500. Okay, and so after you use the rigid body equilibrium, you will find you have only one equation. But the one equation we cannot solve the unknown TA and TB. That's for sure. So you have to find another equation. That's called compatibility equation, or mathematically is a constraint for this problem. So what's the constraint for this problem? It's very similar to axial load we just showed before. Okay, so I apply a torque here. I apply a torque here. Right? Apply a torque here. I will have the angle of twist here. I will have angle twist AC. And I apply a torque here. I also have the angle twist in CB. Okay, understand that? I apply a torque here. I will have the deformation. I will have the angle twist in AC section. And also, this torque will have the deformation angle of twist at the CB section. Okay, I call it CB. okay, angle twist, and the torque and overall the angle, the overall deformation of the angle must be equal to 0. Understand? Okay, here is some explanation from the textbook. You see, this will have the angle twist. This the angle twist in this section and this section is just opposite. You see that? For example, for this one, angle twist is twist, maybe it's twist this way and this is twist in that way. Okay, see that? You see the rotation here, the angle twist, maybe the angle twist in this section is this direction, the angle twist in this section is this direction. And overall, because it's claimed the bar is confined in the terminal AB, so the overall deformation must be 0. Okay, that's the constraint or competitivity equation of this problem. Okay, so angle formula for angle twist? Do you remember that? Okay, so it's T and TC over GJ, right? GJ TC. Let me check. Oh, TL over GJ. TL over GJ. Okay. So for 5AC, okay, so 5AC, so AC, the angle twists are AC section. We need to know the torque in AC section and the L for AC section, and the shear modulus for AC section, and the moment, polar moment of inertia AC section, and plus we need to know the torque on CB section and the length of CB section and shear modulus of CB section times the polar moment of area under CB section. Okay, and this is on the same bar. So GAC equal GCB equal to G. Let's assume its shear modulus is G. And this cross section area doesn't change, okay, along this bar. So JAC equal to JCB, and we just call it J. So here the equation will become, okay, the equation will become right here. So you will have the TAC times LAC divided by GJ plus GJ, and TCB times LCB equal to 0. And we multiply GJ on this equation. So you will finally have TAC times LAC plus TCB times LCB equal to 0. And LAC is 3, okay, and LCB is 2, okay. So the only thing we left we need to know. Okay, right now we only thing we have to solve is find out TA connection between TAC and TCB and the TA and TB. Okay, find a relationship between the TAC, TCB, and TA and TB. So how to do that? How to do that? Yeah, just like we did in axial loading member with cut section method. Okay, we cut. So we need to know the TAC and TCB. So we need to cut section maybe here, okay, here, and here. Okay, so this is C, right? Yeah, this is C. C is here. So we need AC section and the CB section. So we need to cut here AC between AC and between CB. So let's start from the first one. Okay, so this here is so this is TA. And here the section AC, TAC. Yeah, once again, I don't know the direction or direction of the torque AC. So I just assume everything is counterclockwise. So I assume everything is counterclockwise. So it's TAC. Okay, so the other section is here. Okay, here is another section. This TA and the C is here. So here is 500. And here I don't know the direction of torque of CB. So I just assume everything is positive. So the torque CB. Okay. So okay, we have so we have this. Okay, so I just erase here. Okay. Okay, so we did and then we did the moment balance on each section. So here you will have For here, you will have what a balance equation. What do you have? You will have the TA plus TAC is equal to 0, and that tell you TAC is equal to minus TA. And here, what do you have? You have TA plus 500 and plus TCB and equal to 0. Okay, because everything is static in this course, so the moment must be balanced. Okay, the total moment must be 0 in this problem. So what this tell you, okay, the TCB is equal to minus TA minus 500. Okay, so you got this too. Okay, you see the magic? Yeah, see the magic here. See the magic here. So you put these two back into this to the competitivity equation. You just uh, you just derive. Okay, so finally, what we will have? Okay, put everything in there. So TAC equal to minus TA and times 3, and TCB is minus TA minus 500 times 2 and times 2 and equal to 0. So what this will have? You will have minus 3 minus 2. You have minus 5 TA minus 5TA minus 1000 equal to 0. So you will have the TA equal to minus 1 and minus 200. Okay, and you have TA. What's your TB? Because TA plus TB is minus 500. So you have TB is equal to minus 300. Okay, so what's this answer tell you? Okay, so we assume TA and TB is all counterclockwise. Okay, but we got a negative value. We got TA and TB a negative value, so that means the real direction of the torque is okay. The real direction of the torque, maybe I draw it here. The real direction of the torque is, yeah, initially with TA and TB we assume counterclockwise, but we got negative value. But so the real direction is clockwise, and TA is 200 Newton times meter, and TB is 300 Newton times meter. So let me check the answer. Did I answer right? Okay, TB is 300. Okay, TA is 200. And it's clockwise. Yes, I did it right. Okay, so that's the very simple. That's the basic example of the statically indeterminate in torsional member. Yeah, I also have some statically indeterminate problem for torsional load member. I think 2 or 3 problems, and I have recorded some video. So please watch the video and solve this statically indeterminate problem by yourself, because they are similar, really similar to each other. So I don't want to explain it one by one in class. They are very similar to each other. Yeah, the competitivity equation, it's not really that hard. Okay. Okay. So I just start video here. Okay. See you in the next video. Bye bye. Okay. Let's start it.